Lab 1, and I am Jaden Wataki. So, as a quick introduction, constant velocity is exactly what it says. An object moving at a constant rate for a certain period of time. This works off of Newton's first law of motion, which states that an object in motion will remain in motion unless it is acted upon by an outside force. This outside force could be friction or some other object. For this lab, we will mostly be dealing with friction as the ball moves along its path. We can see some equations for updating the velocity as well as updating the position, but this will come in handy later when we are analyzing the code snippets. So this experiment. So for this experiment, I rolled a lacrosse ball across the floor and I recorded its movement. The ball is initially pushed, and the ball gains a slight edge in speed as opposed to the average velocity of the movement, seen in the fact that the initial velocity is 1.03 in the reverse direction as moving from right to left in the video, but becomes 0.95 in the same direction, right to left, on average. This can be attributed to forces acting on the ball after the fact that I pushed it. So it comes back to speed. So this is analysis of the motion. As you can see, we tracked the ball using the point mass feature of Tracker. And originally we set up a coordinate axis that the ball moves along, and at each step we record the point mass of that step, which can be shown in the chart in the bottom right, and that will be used to compare to our computational model in the future. So here are some snippets from the code. The initial position can be 0.00100. This is from our tracker data, and the velocity also comes from our tracker data using the first 2 points, and this gives us negative 1.0300. We can calculate the velocity at each step using the formulas from the first slide, which are shown in the second code snippet. After running this code, we get the following position versus time graph and velocity versus time graph. This position versus time graph is expected because it is moving from right to left at a constant rate, so it is a negative slope, and the velocity versus time graph will be at this because it is constant velocity. It doesn't change. So this is where we compare our model to the tracker data. Originally, the model and the tracker data have the same slope, but as time goes on, the tracker data flattens out due to friction or any other outside forces that are not accounted for from the model. The model continues to go pretty much a straight line, but you can see that the tracker data kind of goes like up more so than the model data. So what ifs? What if we flipped the axes? So if we flipped the axes, the results would be the same, except for the fact that the slope of the position versus time graph would move constantly in the positive direction and not the negative. However, the results would end up being the same, seeing that the model overpredicts and does not consider friction and other forces on the ball. Is the zero net force justified? Considering the friction we saw in the tracker data, a zero net force is not justified as this does not account for real-life situations. But it is good for getting a good estimate of what could happen if we weren't able to run a simulation.